Hey scholars, so I wanted to go over a few things to help you with the periodic trends quiz. So a couple of things that I wanted to go over, which is what are the different blocks. So as you can see, I've drawn the periodic table here, and this is your S block. So any element in this little, in these two columns or helium up here, they will all be considered part of the S block. All of these elements that are in the middle will be considered part of the D block. But there's another name for these D block elements. They're called transition metals. So right here you see that I've labeled group 3 to group 12 as transition metals. So these D block elements are also known as transition metals. Then we have our P block, which is all the way here on the right. So all of these elements are in the P block. So remember, blocks are also the same as suborbitals. So this is the P sub, all these elements will have electrons in the P suborbital, or they're known as P block. And then all the ones in the bottom here are in the F block, all these elements. And the F block is also known as inner transition metals. So D block is known as transition metals, F block is known as inner transition metals. In addition, there are a few special groups. So group 1 right here is your alkali metals. So this entire group here is your alkali metals. And then your group 2 is your alkaline earth metals. So all of these right here are your alkaline earth metals, and you can see that I've labeled that in the bottom. So group 1 is alkaline metals, group 2 is alkaline earth metals. Group 18 are your noble gases. So all of these guys here are going to be your noble gases. And then your group 17 is your halogens. So halogens, and I've written it here. So 17, group 17 is your halogens. And then your group 16, which is where your oxygen is located, your oxygen group is called your chalcogens. That sounds like halogens, but it's spelled CHALCOGENS, chalcogens. So they are a special group that's right here. So that's group 16, or your oxygen group is known as chalcogens. So you'll have to characterize the elements that you have in that periodic trends quiz as to which group they fall into. But sometimes you might also get a period 5 element, and you're like, what does that mean? Well, if they're in row number 5, so if they're in row 5, that means they can be a period 5 element. So sometimes you won't be characterizing them as a period 5 element. It depends on what words are there and what you've already used up and what you still need to use up. So, but if they're in row 5, you can call them a period 5 element. Not a periodic 5 element, a period 5 element. Let me erase that. So it can be a row 5 element is the same as a period 5 element. So that's something that you can say. Okay, so that's one thing. The second thing I also wanted to talk about is there are some categorizations you have to make according to the valence electrons. So those valence electrons are the outermost electrons. Outermost electrons. And so what you have to remember is when we're talking about outermost electrons, we skip the D block and we also actually skip the F block. So we don't talk about D and F when we talk about outermost electrons. So when we really talk about outermost electrons, we're only talking about column 1, 2, and then column 13, 14, 15, 16, 17, and 18. So column 1 will have 1 valence electrons. Column 2 will have 2 valence electron. Then we skip the entire D block. Column 13 will have 3 valence electron. Column 14 will have 4. Column 15 will have 5. Column 16 will have 6. Column 17 will have 7, and column 18 will have 8. So I'm going to label them up here as well. So column 1 will have 1 electron, Column 2 will have 2 valence electrons. Column 13 will have 3 valence electrons. Column 14 will have 4 valence electrons. Column 15 will have 5 valence electrons. Column 16, 6 valence electrons. 7 for column 17. And column 18 will have 8 valence electrons. And remember, all our elements want to have those magical 8 electrons because that is the octet rule. They want to all have 8 electrons. And if they have 8 electrons, they're going to be happy. They're not really going to be super reactive. They're not going to want to bond because they already have those 8 electrons. So they have no reason to share electrons or give up electrons or to, attract electrons. They don't need to do any of that because they have the 8 which they want. So that is regarding valence electrons. So sometimes if, for example, an element is in column number 13, you might have to say, oh, it has 3 valence electrons. That might be what you will characterize it as. So these are the different categories that are there to help you with the periodic trends quiz. I wanted to show you was really to kind of explain to you what is the trend for atomic radius. So we already kind of talked about in class the fact that the general trend, so when you talk about the group, the atomic radius decreases as you go down a column or a group. And then when you talk about your period trend, your atomic radius increases from right to left. So this is your period trend down here. Up there is your group trend. But then on the quiz, what you'll notice, it would ask you like precisely why these trends are in place. So you need to know the reason. So the reason that the atomic radius increases as you go down a group is as you're going down a group, you're adding more energy levels. So that's why I've drawn these circles here. So when you're in row number 1, for example, you'll just have 1 circle because you have 1 energy level. When you're in row number 2, you'll have 2 circles, meaning 2 energy levels. When you're in row 3, you'll have 3 energy levels. When you're in row 4, you'll have 4 energy levels. So 4 different circles. So the atomic radius increases as you go down a group because you are adding energy levels, adding number of energy levels. Okay, so you keep adding energy levels, so the atomic radius increases. So for example, if there's a question that says which of these atoms is bigger and you pick the bigger one, you'll say it's bigger because it has more energy levels. Suppose it says which of these atoms is smaller, you'll pick the one that's smaller and you'll say it's smaller because it has fewer energy levels. So it's bigger because it has more energy levels, and it's smaller because it has fewer energy levels. But that's only that reason, that energy level reason can be used. So when it says why is it smaller or bigger, that reason can only be used when you're talking about elements that are in the same group or same column. What about elements that are in the same row? So when you're talking about elements that are in the same row, what you have to keep in mind is that you have to you're not changing the number of energy levels when you're in the same row, because remember, if you're in row number 4, you have 4 circles. If you're in row number 3, you have 3 circles. So what about elements that are right or left of each other but are in the same row? So for elements that are right or left of each other, the reason that you will be increasing or decreasing the atomic radius is because of the fact that you're adding more protons without adding energy levels. So when you add more protons without adding energy levels, what happens is you change the effective nuclear charge. So the number of protons, when you change the number of protons, you're making the nucleus more positive. So you're giving the nucleus more charge. So that's why you're increasing the effective nuclear charge. So for example, if you have 2 elements, let's say you have element F and C. So F is located here on the periodic table, and then C is located here on the periodic table. And now if I ask you which one is bigger, you would say that C is bigger because C is more towards the left. And remember, that's how our trend goes. Our trend increases in this direction. So if C is bigger and it asks you why it's bigger, C is bigger because it has a smaller effective nuclear charge. Okay? So the higher the nuclear charge, the smaller the atom is going to be. The higher the effective nuclear charge, the smaller the atom is going to be. Because as you increase the number of protons, you're literally making the nucleus more powerful. You're making the nucleus like a bigger magnet. So as you increase the number of protons, your nucleus is able to pull all those electrons in more and more. And when it's able to pull those electrons in some more, it makes the atom smaller. When you have few protons, they're not able to pull the electrons very effectively. So if they're not able to pull the electrons very effectively, you're going to have a bigger atom. But when you're able to pull all those electrons in because you've added so many protons, then the atom becomes smaller. So the higher the nuclear charge, the smaller the atom. Okay? And the smaller the effective nuclear charge, the larger the atom. So this is something to keep in mind. So smaller effective nuclear charge means larger atom. Larger effective nuclear charge means smaller atom. So when it's talking about the period trend for atomic radius, the reason you'll say why is it bigger or why is it smaller, you're going to talk about nuclear charge. When it's talking about the group trend, meaning how it changes up and down a column, you are going to talk about the fact that there's more energy levels or fewer energy levels. The more the energy levels, the bigger the atom. The fewer the energy levels, the smaller the atom. And as you keep going to the next row, you'll be adding more and more circles or more and more energy levels. So that is regarding atomic radius. Now, when we talk about electronegativity, so in electronegativity also there's a group trend and a period trend. So in electronegativity, remember electronegativity is the ability of an atom to attract an electron. Attract and an electron. Okay, so as you go up a group, the electronegativity increases. As you go from left to right, the electronegativity increases. So the group trend is as you go up, it increases. The periodic trend is as you go from left to right, it increases. So the reasons for each of these, so if you have two elements that are in the same group and they're asking you which one has more electronegativity, the reason you're going to give for that is shielding. If you have two elements in the same period and they're asking which one has more electronegativity, the reason you're going to give for that is nuclear charge. So basically, if you think of electronegativity, think of all of these protons that are in the nucleus. You have all of these protons and you have all of these neutrons, and then you have all these circles around the nucleus where the electrons are located. Electronegativity is the ability of an atom to attract a new electron, an electron from the outside. So it's able to attract that electron from the outside. So essentially, it's able to attract this electron from the outside if it doesn't have too many energy levels. If there's so many energy levels and there's so many electrons to already like attract and keep close to the nucleus, then the nucleus is not going to have any more strength to be able to attract that outside electron. So the way you can think about it is more energy levels, there's more barriers. And if there's more barriers, your protons are not going to be able to attract all those outside electrons. And so when you have less shielding, meaning you have fewer energy levels, then your electronegativity is going to be really high. So less shielding means higher electronegativity, because less shielding means that those that those protons are able to attract the electrons on the outside, because there's very few energy levels that are like preventing them, or very few barriers that are preventing them from, exerting force on those outside electrons. But when you have lots of energy levels and lots of electrons that they have to kind of keep in place, then they're not able to attract any more outside electrons. So when it tries to attract this outside electron, this force is weak. Strong, because not that many energy levels to get through to attract this outside electron. But this force is weak because there's so many different energy levels it has to go through to attract that outside electron. Right? I put the negative sign on there because it's an electron. And so when you're talking about the group trend, less shielding, so less number of energy levels will lead to higher electronegativity. More energy levels, electronegativity, more shielding will lead to less electronegativity, because less ability to attract that outside electron. When we are talking about a period, remember, when you're in the same row, the number of energy levels do not change. So you cannot use anything that has to do with energy levels to justify why something has lower or higher electronegativity. Only when you talk about a group can you say anything about energy levels, because only when you go up and down a group do the energy levels change. So you can use the energy levels reasoning and the shielding reasoning only when you're talking about a group. When two elements are in the same group, meaning same column, only then you can say it's shielding or it's energy levels. If it's in the same period, they're not going to have different energy levels. They're going to have the same number of circles holding electrons outside them. So when they're in the same row or same period, you cannot talk about shielding or energy levels. If they're in the same period, the reason for lower or higher electronegativity is going to be, again, that effective nuclear charge, which is when you're adding extra protons. Remember, the atomic number is changing as you go across a period because you're adding extra protons, but you're not changing the energy level. The energy level is staying the same, but you're adding extra protons. So you're giving the nucleus more force. You're making it a stronger magnet, so it's able to attract more electrons. And so if you have a higher effective nuclear charge, you're going to have a higher electronegativity. And if you have a lower effective nuclear charge, lower effective nuclear charge, you're going to have a lower electronegativity. And the amount of nuclear charge you have is just dependent on the number of protons you have. The more protons you have, the higher the nuclear charge, because the nucleus is made up of protons, and protons are what have the charge. So lastly, we are going to be talking about ionization energy. And remember, ionization energy is the amount of energy needed to pluck an electron, basically pluck/remove an electron from an atom. And it's going to be the outermost electron. Pluck an electron from an atom. You're not going to try to pluck an electron that's like really close to the nucleus, because that's going to be difficult. You're going to try to pluck the electron that's farthest away. So basically, what is the amount of energy needed to pluck the electron that's farthest away from the nucleus, from an atom? Okay, and this follows the same trend as electronegativity. You need more more ionization energy as you go up a group, meaning up a column, and you need more ionization energy as you move from left to right. Okay, and the reason you're going to give for this electronegativity, this ionization energy change, is, when you're talking about two elements that are in the same group, you're going to say it's because of shielding. Remember that shielding and that energy levels go together. Shielding and energy level reasoning can only be used when two elements are in the same group. The more protons and effective nuclear charge reasoning can only be used when you're talking about things that are in the same row. So here, when they're in the same group or same column, if there is less shielding, you're going to need more ionization energy. If there's more shielding, you're going to need less ionization energy. So the way you can think about it is, when you have protons inside the nucleus, then you have all these energy levels and the electrons on the outside. The farther the electron is away from the nucleus, the easier it is to be able to pluck it off. So for example, let's say we have this atom that has these protons and it has these neutrons with no charge, and then let's say it has 1, 2, 3, 4 different energy levels. So these protons have to pull all of the electrons on all of these energy levels. So this electron that's on the outside, on the last energy level, is going to be fairly easy to pluck off. You're going to need little bit of energy, just a little energy, to pluck off these electrons, because of the fact that this nucleus is so shielded, because there are so many other electrons that it is pulling on, that it's not able to exert a lot of force on this electron that's all the way on the outside. So that's because this nucleus has all of these other electrons that it's trying to pull on, and so it's busy exerting force to be pulling on all of these electrons, so it doesn't have that much force to exert on this final electron at the end right here. So this electron is going to be fairly easy to pluck off. So, and this is basically called shielding, because all of these other electrons, which are going to take up the nucleus's force and energy, are going to shield that outside electron from having that much force exerted on it. So it's not going to have a lot of force exerted on it from the nucleus, and so it's going to be easy to pluck it off. So the less shielding there is, so for example, if you're talking about this atom, this has less shielding, it just has 2 energy levels, so it's going to be hard, so difficult. So pluck it off, it's going to be difficult here. So pluck this electron off is going to be difficult because there's only 2 energy levels. Those protons are able to pull that electron as well. They don't have much to concentrate on. They're like, oh, I can pull that electron as well. So it's going to be difficult to pluck it off. But these protons down here have so many other electrons that they have to concentrate on, and so many other electrons that they have to kind of pull, that they're not able to exert that much force on that outside electron, and so it's going to be easier to pull it off. So the more the shielding, so here you have more shielding, less the ionization energy needed. Less shielding, like up here, you're going to need you're not going to it's going to be difficult to pluck it off. So less shielding, you're going to need more energy. Okay, so more shielding, little energy, less shielding, more energy, and that's what I've written here as well. So less shielding, more ionization energy, more shielding, less ionization energy. So it's going to be the opposite of what is happening with shielding. If there's more shielding, then it's going to be easy to pluck that off. If there's less shielding, then those protons are going to be like, I'm holding on to these electrons, you can't pluck it off. So that is the group trend. So that's what's happening when you're going up and down a group, because remember, only when you go up and down a group do you change the amount of shells or circles or energy levels. But what happens when you're in the same period, meaning you're in the same row? At that point, you're just adding protons without adding energy levels. So when you add more protons, you increase the effective nuclear charge. Increasing the effective nuclear charge increases the amount of ionization energy needed. So as you increase the nuclear charge, it's like you're giving the nucleus a bigger magnet. The nucleus is now has more protons, so it's able to pull those electrons more effectively. When it didn't have that many protons, it was not able to pull those electrons more effectively. So as you increase the effective nuclear charge, meaning as you add more protons, you're going to need more ionization energy. As you decrease the effective nuclear charge, meaning as you decrease the number of protons, you're going to need less ionization energy. So I hope that helps you with the periodic trends quiz. I'm also going to be creating a lecture for you on electron configuration.